Okay, in this video we're going to focus on the role of sample size in influencing variability in your data, and more importantly, how it influences the standard error and confidence intervals around the mean in a normal distribution. I've got some opioid death rates on average for different regions of the country here to display real quick. So the data are a little old. It was originally among different areas of the country, first highest in the New England area. The states that are defined as New England initially, this is not true now. There are other regions where the opioid death rates are higher. But in this example here, you can see that the mean opioid death rate was 20 per something like 100,000 or whatever it might be in the New England states. There was variability in the New England states depicted by these bars, and some states like the Pacific had less variability among their states, and our estimate of the true mean death rate for folks in this region is depicted by this dot here, and the true mean death rate for the states and the folks in this region, the West North Central region where it's the lowest, is depicted here. We are 95% confident that it's in this range, and this is our best estimate right here. So let's do a little application and figure out how to shrink these bars or what factors may increase the size of these bars. As you would recall, when we're calculating confidence intervals, we multiply 1.96 for the 95% confidence interval. So we multiply the mean plus or minus 1.96 times the standard error. So if you have a lot of error, when you make that multiplication by 1.96, that error is going to double and show up in your confidence interval above and below the number. All right. So using some Excel data, we're going to randomly generate some data. And this formula here that I've got, you may not see it very well, but it's normal inverse of random numbers between a certain range. The mean, standard deviation are depicted here. So I'm telling it to generate random numbers following a normal distribution where the standard deviation is 0.4 and 2.93 is our target measure of central tendency. We'll call these average GPAs for a university, and we'll say that maybe there's 6,000 people at the university. So in this first sample, we may sample just 14 people. So it randomly generated 14 people. Their GPAs, they ranged here from, this first number was 2.89, the last number was 2.78, and we've got numbers all in between. I'm going to take that data, I'm going to clear Stata out, data editor, and I'm going to paste these observations for this small set right here. There were 13 observations reported. We're going to then, I'm going to keep this command. I'm going to delete this column, and we're going to go with a medium size distribution. A medium size amount of numbers. Same formula, but this time we're going to maybe get data on 138 or so folks. So I'm going to copy this data, paste it into Excel. So I pasted it there. So it says 137 observations were pasted in. I'm going to copy our command again here in Excel. Delete this column. I'm going to have a column called large. got the random number generator for the normal distribution going in here. And this time we're going to get like, we'll say 2,000 people to make inferences about maybe a population of 20,000 people or 10,000 people. We don't know. So we'll put 2,000 people in here. Okay, we got like 2010 or so. I'm going to copy these, go to my data editor, and then paste them in to Stata. Stata says 2011 observations were pasted in. Now, the next thing I'm going to do is I'm going to look at the mean for the small, medium, and large. If I want to look at them all together, I need to use the summary command, summary, small, medium, and large. I can look at them all together using sum, and I see the mean for the small data set was 3.01, the medium was 2.91, and the large was 2.939. So it randomly generated them. Now, I told it that 2.93 is the actual average for the distribution. That's what the real distribution is, with a real standard deviation of 0.4. So as you do larger sample sizes, 2.939 is closer to 2.93 than the medium and the small. In fact, the medium is about 2.1 away from it. The large is about 0.9 away from it. So the large is closer to the true population mean. And then the smallest sample, 3.01, it is almost 8 points, or 0.86 GPA points away from, or 0.08 GPA points away. So it's the furthest away from what I plugged in as the true population mean. So you can see that larger sample sizes got closer to the true mean. All of them have similar standard deviations. There's some differences. In fact, the large one had the largest standard deviation, but that doesn't necessarily matter. The confidence intervals will matter a lot. Now, if I do our command means to try to get the actual confidence intervals or the standard errors, I will get some output, but I'm going to show you something that you may not have caught on your own. It might have frustrated you if you've tried to do this. So, one, when I type in means, it gives me arithmetic, geometric, harmonic, and all of that. I don't want means. What if I just do mean? Okay, for the arithmetic mean, it gives me the mean, standard error, and the confidence intervals. But all of them have the same standard error here because it's only based on 13 observations. Okay, in fact, the large one had the highest standard error here when you're only looking at 13 observations. So only the columns of data editor, looking at data editor here, only these first 13 columns were factored into this. So how do I get the mean command to work for each of them? Well, you have to do them individually. So when you do small, it's not going to change. The mean is 3.01, the standard error is 0.077 or 0.0765. Okay, now we're going to do the mean for medium. Mean for medium. It's based on 137 observations. The standard error goes from 0.076 to 0.033. We really made the standard error go down a lot. And the mean is 2.91. Our confidence interval over here, 2.84 to 3.18, over a 0.30 difference there. Confidence interval here, 2.84 to 2.97, only a 0.13 difference. 0.30 difference, 0.13 difference. You can imagine what will happen when we put large in. We put large in, the mean for large, we see the standard error get really small, 0.009, which is way smaller than 0.03 and 0.076. the confidence interval gets much tighter, 2.92 to 2.956, so only 3/1000ths of a difference. And that is just a brief showing of how a large sample size around the same kind of population mean and the same population standard deviation can really be affected by sample size. If you want to double check to see how our sample size looks, I don't know what happened on the on our command log here. Maybe I'll just punch in the command. I was going to look at an actual bar chart, histograms of the various data points. So if we do, or data points, but variables, histogram of the small data set. So it kind of takes on the bell curve a little bit. A histogram of the medium data set. So a little closer to our bell curve. And then when we do a histogram of the large data set, we see it something looks much, much closer to the actual bell curve. So hopefully that makes a little bit of sense. If you wanted to actually plot the, around the histogram, the actual shape, this is for the small one, type freq normal, and it tries to plot the normal curve. We can do it with the large one, histogram large freq normal. I guess it doesn't need the parentheses, that was my mistake. So we see this normal distribution curve. We can test it to see whether or not they fit the normal distribution. And the p-value here is 0.10. So it says that it does behave normal at the large level. At the medium level, it says it's 0.65 for the p-value, meaning no difference from normal. And at the small level, p-value 0.54, no difference. We can do the plot, if you remember the Q norm. You'll see how well it lines up to the line. It actually says that these dots are close enough to that line that they're not different than the normal distribution. We do the Q norm large. The dots are close enough to this line that they're not significantly different. So that's just a little bit about using the sample size as it relates to shrinking the standard error. And we'll look at some examples here in a second with how it relates to the odds ratio and MedCalc to do some simple calculations with some made-up numbers and data. All right, so that concludes all for this video.